Attention is all you need. Part 3. The Transformer Architecture, the Big Picture. In Part 2, we walked through the near misses, convolutions, earlier self-attention ideas, and memory networks, and why none of them fully removed the sequential bottleneck. Now, we finally meet the transformer itself. This is the high-level blueprint, the big picture of how information flows from input to output, before we zoom in on the mechanics. Now, we get to the exciting part. How does the transformer actually work? But before we dive into the technical details, let's step back and look at the overall architecture from a high level. Think of this as meeting the cast of characters before the story unfolds. The encoder-decoder framework. Most competitive neural translation models follow what's called an encoder-decoder structure. This has been the winning formula for years. Here's the basic idea. You have an input sequence. Let's say an English sentence you want to translate to German. Something simple like, "The cat sat on the mat." The encoder reads this input and converts it into a sequence of mathematical representations that capture the meaning of your input. Think of it like translating the sentence into an internal language that the AI understands, a language made of numbers instead of words. Then, the decoder takes these representations and generates the output sequence, your German translation, one piece at a time. And here's a crucial detail. The decoder is autoregressive. That means at each step, it looks at all the pieces it has already generated to help decide what piece comes next. It's like writing a sentence where each new word you write depends on all the words you've written so far. Now, in this context, when I say pieces, what I really mean is tokens. A token is just the AI's way of breaking text into chunks, usually whole words, but sometimes parts of words. So, the cat sat becomes 3 tokens. The cat sat. Simple as that. The transformer follows this same overall encoder-decoder structure, but with one key difference. Instead of using RNNs, those older models that had to process words one by one, it uses stacked self-attention and feed-forward layers for both the encoder and the decoder. We'll explain what those mean in just a moment. Let's walk through the 2 stacks, starting with the encoder. The encoder stack. Building understanding. Picture the encoder as a stack of 6 identical layers, like a tower where each floor performs the same operations. Each layer has 2 main parts. Let me walk you through them. The first part is multi-head self-attention. This is where each word can look at all other words in the input. Each word can essentially ask, to understand myself, which other words should I pay attention to? For example, in the sentence, "The animal didn't cross the street because it was too tired," the word "it" needs to connect back to animal. Self-attention makes that kind of link easy, even though animal and it are far apart in the sentence. The second part is a position-wise feed-forward network. Think of this as a mini calculator that works on each word individually. After attention connects the words together, this network refines what each word means in this specific context. When I say position-wise, I just mean it processes each word's representation separately. Now, around each of these sublayers, the model uses 2 stabilizing techniques. The first is called residual connections. These are shortcuts that help information flow smoothly through the stack. The second is layer normalization. This keeps the numbers well-behaved so training doesn't break down. You don't need the details of those yet. Just remember, each encoder layer repeats the same 2 operations, self-attention, then feed-forward, with stabilizers wrapped around them. So our sentence, the cat sat on the mat, passes through this 6-layer stack. At each layer, the words become more context-aware. By the end, the model has built a deep understanding of what the sentence means. Now let's look at the decoder. The decoder stack, generating the output. The decoder is also a stack of 6 identical layers, similar to the encoder. But each decoder layer has 3 sublayers instead of 2. Let me explain each one. The first sublayer is masked multi-head self-attention. This is self-attention, but with one key constraint. When predicting the next word, the decoder is not allowed to look ahead. It can only see the words it has already generated. Why? Because when it's generating Katze, the German word for cat, it hasn't generated the rest of the translation yet. It can't peek at the future. The second sublayer is encoder-decoder attention, often called cross-attention. This is where the decoder looks back at the encoder's output, those mathematical representations of the input sentence, to decide what to generate next. It's like translating with the source text open beside you. While you're writing Die Katze, you can glance back at any part of the cat sat on the mat to make sure you're capturing the right meaning. The third sublayer is a position-wise feed-forward network, just like the encoder. That same mini-calculator, refining the representation. And just like the encoder, each sublayer is wrapped with residual connections and layer normalization to keep this deep stack trainable. So to recap, the decoder has masked self-attention over what it's generated, cross-attention back to the input, and feed-forward refinement. 3 operations per layer, 6 layers total. The supporting cast. There are a few other components that sit at the edges of this architecture. Let's slow down here because these can sound intimidating, but they're actually quite simple. First, input and output embeddings. Remember how I said the AI needs to convert words into numbers? That's what embeddings do. They turn each token, each word or word piece, into a list of numbers called a vector. You can think of a vector as coordinates in a high-dimensional space where words with similar meanings end up close together. So, cat and dog might have similar vectors because they're both animals, while cat and table would be far apart. Second, positional encodings. Here's a problem. Attention lets every word look at every other word simultaneously, which is great. But that means the model has no built-in sense of word order. It doesn't know that the cat sat is different from sat cat the. So we add positional information, a special mathematical pattern that tells the model where each word sits in the sentence. The first word gets one pattern, the second word gets another, and so on. Third, at the very top of the decoder, after all 6 layers have done their work, there's a final linear layer. Think of it as one more calculation, followed by something called softmax. This converts the decoder's final representation into probabilities over every possible next word. So the model might output 90% confident the next word is mat, 5% confident it's floor, 3% confident it's rug, and so on. Those are the supporting components. Now let's see how everything flows together. Let's trace our example sentence all the way through the transformer. We'll start with the encoder side, then move to the decoder. First, the encoder. Our English sentence, "The cat sat on the mat," arrives as input. The first thing that happens is each word becomes an embedding. Remember, that's just converting words into numerical vectors, lists of numbers the model can actually work with. So we've got the, cat, sat, on, the, mat, all now represented as vectors. Next, The model adds positional information. This is crucial because attention doesn't have a built-in sense of word order. The positional encoding is what tells the model. The is first, cat is second, sat is third, and so on. Now here's where the real work happens. This sequence passes through 6 encoder layers, one after another. At each layer, the words become more context-aware. The first layer might start connecting cat with sat. By the third layer, maybe it's building richer relationships. By the 6th layer, the model has built a rich, deep understanding of what the sentence means. By the end of those 6 layers, we have a complete mathematical representation of the English sentence. Think of it as the sentence's meaning encoded in numbers. That's the encoder done. Now let's move to the decoder. The decoder works differently because it's generating the translation one word at a time. At the very start, the decoder doesn't have any German words yet, so it begins with a special start of sentence token. Just a signal that says, OK, translation is beginning. This token becomes an embedding, just like in the encoder. Positional information gets added. Then it passes through 6 decoder layers. But remember, decoder layers have 3 operations, not 2. The first operation is masked self-attention. Since we only have the start token right now, there's not much to attend to yet. But this mechanism will become important once we've generated a few words. The second operation is cross-attention. This is the crucial one. The decoder looks back at the encoder's output, that mathematical understanding of the cat sat on the mat, and uses it to decide what German word should come first. The third operation is the feed-forward network, refining the representation. After all 6 decoder layers, there's one final step. A linear layer and softmax convert everything into probabilities. The model might say, I'm 90% confident the first word should be die, 5% confident it should be dare, 3% confident something else. Let's say it picks die. That's the first word of our German translation. Now the whole thing repeats, but with more context. The decoder now has die as input. This becomes an embedding. Positional encoding is added, and it flows through those 6 decoder layers again. In masked self-attention, the model can look at die, the word it just generated. In cross-attention, it looks back at the cat sat on the mat again, consulting the source. Feed-forward refinement happens. And at the top, softmax predicts the next word. Let's say it outputs Katze, the German word for cat. The pattern continues. Now the decoder has die Katze as input. Through the 6 layers again. Masked self-attention over die Katze. Cross-attention back to the English. Feed forward. Softmax predicts SAS, which means sat. Then die Katze SAS becomes the input. The decoder generates auf. Then die Katze saß auf generates der. Then die Katze saß auf der generates Mathe. Finally, the model outputs a special end-of-sentence token, signaling that the translation is complete. And there you have it. Die Katze saß auf der Matte. The cat sat on the mat. So to recap the full flow, the encoder processes the entire English sentence in parallel, building a deep understanding through 6 layers of attention and feed-forward networks. The decoder then generates the German translation one word at a time, with each word depending on what came before and constantly checking back with the encoder to make sure it's capturing the right meaning. Why this architecture works? The key advantage is that the encoder can process the whole input in parallel. Attention gives direct connections between any 2 positions. It can look directly at animal, without passing information through a long step-by-step chain like the old RNN models had to. The decoder still has to generate words sequentially. You can't generate word 10 before word 9, but attention lets each step pull relevant information directly from both the earlier outputs and the source sentence. It's this combination, parallel processing in the encoder, direct connections everywhere through attention, and the decoder's ability to look back at exactly what it needs, that makes the transformer so powerful. Next, in Part 4, we'll open up the attention mechanism itself and see exactly how it works inside.